You should start taking notes. Your exam is coming up soon on basic cell structures, and we're going to make sure we know our cell structures and differences between cells. It's one of the major objectives in this unit. So there's really two objectives in this unit. The first is to understand the cell and all its different structures. And function. And that's the title of the chapter, Chapter 7, which you should have read already. You were asked to read and make index cards, or those foldables. I sent you a video on how to make the foldables. Could anyone who's done, I see a lot of people have, could you show everyone what you've done? Hold them up. If you've done it, hold it up. So here we have examples. There should be a number of these. It shouldn't just be one or two. There you go. Look back here. Look how many she has. All right. Cutting them all the way on cutting both slips of paper is going to be an issue for you in the long run. And you can see Frank has a lot as well. Because you all did the vocabulary from the video and you did the Chapter 7 vocabulary, the important words that you thought you were going to have trouble remembering. So at this point, you should, when we start to discuss this, because you read it, because you've made index cards, it should be evident that this is what is important and what is not important. When you see some word that you have on your foldable, when you see some word that you remember from the chapter reading, you should put an extra asterisk on it, highlight it, do something, make a note that this is probably going to be something that's going to be tested. So the second thing is, and it's really just a subunit of structure and functions, is how do things move in and out of a cell. So those are two major objectives, and there's a lot to learn in order to understand these two major, well, let's call them goals. Big, broad goals. These are our goal at the end of the unit. Your goal is to make sure you understand these two things. How do things move in and out of the cell, and all the different structures and functions of all the different cell types. And if you know these two, it's going to be about 14% of your Ohio State test. It's going to be a good portion of any question you get that's science-based on a standardized exam is going to be based a lot on these ideas. So let's move on. We've talked a lot about these things. Anybody tell me what they are? What is this representing? At this point, everyone should be automatically saying, without looking up, phosphate and fatty acid. Let me use a different color. Two of them, 1, 2. To make a phospholipid. That is a phospholipid. It's the basis of a cell membrane. It's the first structure that had to form for life on Earth to start. Via a bunch of different experiments, already did a very interesting experiment early on that we talked about, but during various experiments, we know that these phospholipids had to come first with a hydrophilic head and a hydrophobic tail. It had to have this for the following reason. If you have a bunch of water molecules in a solution yeah. Yeah, that's just water. You can draw water. If you can't draw water, you guys need to start drawing it a little. You guys have to start practicing a little bit. But this is, you have to keep up. It's H2O, water. And you have a bunch of them now. You have to consider that there's probably billions of these in a glass of water. It's just all hanging out with each other, and they're always moving. They're always moving. You know that from middle school, that things are always moving. Things have kinetic energy. Do you remember kinetic energy? Yes? Yes or no? Yes or no would be helpful. Yes, okay. Thank you. So, kinetic energy, as you remember from middle school, is equal to 1/2 mv squared, where v is movement. Here, this is mass. You know that each of these atoms have atomic mass. They're all moving all the time. Even when something's sitting still, you think that that table is not moving. It's moving. It's vibrating. They're really tiny vibrations, but they're vibrating. Right now, you're going thousands of miles an hour. Over 1,000 miles an hour, you're moving at this second. Every second, every day on planet Earth. You go around the planet one time every day, don't you? You move around this whole planet one time every day. Correct? Yes or no? I'm seeing confusion in your eyes. Do you not move around this planet one time every day? Yes or no? Why do you say yes? Why do you say yes? Because why? Why are you moving around this planet once a day? Why? I'm asking you because the answer is simple. I'm not asking you because it's difficult, or it shouldn't take you that much thought. Think. Why are you moving around? Did you find them all? You took everything out of the whole cabinet.
Yes.
All these books out of that whole cabinet. There's only 2 of them in there.
Yes.
There's something wrong.
Most of them were Unit 4.
Yeah, I got you. Put it back. I'm sure that there's more in there, but I'm gonna come back to it. Yeah, the unopened ones.
I didn't know you wanted us to do that.
Yeah, the unopened ones. They're unopened. Not the open one. I knew there were more in there. Ladies and gentlemen, does this planet not turn on its axes? Yes or no? How long does it take to turn on its axes? People, you're not. It's too early in the morning not to be tired. 5 days. It takes 5 days for the Earth to turn around. What do you mean it doesn't make sense? Yeah, it's not too early. You just want. I said it's too early for you to be tired. It's not too early for you to be awake. It can be both. Think. The Earth is turning around. How long does it take for it to turn around? 5 days. Thank you for guessing. I appreciate it. It's not 5 days. 5 days is wrong.
That's all she just said. 365 days.
It's not 365 days. It's 24 hours. 1 day. One day to turn around its axes. That's what we call a day. When the sun rises, the sun's not moving, we're moving towards it. Is that clear to everyone?
That's very much clear.
No? Okay, I'm asking. I can't hear you. You guys are mumbling. So we're turning on its axis 24 hours, one day. When you see the sunrise, it's because you see the sun in the background as you are a dot on the planet, as you see the sun rise, as you move towards it. Is that clear to you? That should have been taught to you in middle school. I'm sure it was. You may not remember it, but I'm sure it was. Then every 364 and a quarter days, this planet moves around the sun. So it's revolving, spinning on its axis, and I'm sorry, yeah, that's right. What's the other one? What's the other word? And it orbits the sun as well. Okay? Huh? There's two words. No, it's for sure it's moving towards the east. So everything's moving from the very planet moving around the sun to the planet spinning, moving 1,000 miles an hour, moving thousands and tens of thousands of miles an hour as it goes around the sun. Everything's moving. No, you're sitting somewhere else today. You're sitting over there. That table, second table, I'm pointing. I'm pointing. That's your permanent seat. I'm pointing. That's it? Yeah, pick a seat. Permanent seat. Thank you. So, everything's moving, including all these water molecules. They're vibrating. Now, this is going to be a very important idea. They're moving in both directions. They're vibrating back and forth constantly. There's no question that they're vibrating. They're turning, they're spinning, they're moving. Nothing's standing still, ever. So, you're going to take, if you place these molecules that have a hydrophilic. What does hydrophilic mean? You read the chapter, you've listened to class, you've taken notes, you made index cards. Hydrophilic, what does it mean? And then another side is hydrophilic and it's hydrophobic. Correct. Somebody remembers. Hydrophilic and hydrophobic. If you don't have this in your notes because you've been coming in late, because you have been absent, because whatever, then get it in your notes. You need it. You need to know it. I'm about to tell you. Again. So this phosphate, remember it's a phosphorus with 4 oxygens, and it's attached to a carbon. One of the oxygens is attached to a carbon down here. There's a negative. Hold on a second. I'm probably going to say yes to you, but hold on a second. Okay. This is phosphate, and phosphate has a charge. And we talked about that last time as a negative charge. And this is a long chain of carbons. This would be a saturated. This is a saturated fatty acid, long chain of carbons, saturated. Meaning no double bonds, correct? Correct? We remember that?
Correct.
And this one here is another long chain of carbons, except this one's going to have a double bond. I decided it's going to have a double bond. And double bonds are shorter, so that means that they're going to they're going to bend. Let me make it a little more exaggerated so you can see it clearer. It's going to bend the fatty acid away. It's going to make the fatty acid kick out. Do you see it? This one's straight, this one kicks out. Do you see that? Because if you don't see that, it's going to be really hard for you to understand what's going to happen in this membrane. Then this hydrophobic and hydrophilic, what does that mean? That means when we look at water, as we discussed before, water is polar because water is that greedy Mendoza that likes to pull on the electrons. And it's going to be that partially negative and partially positive. It's going to have two poles, correct? Yes? Do you see that? Two sides. It's going to have two sides. One side is going to be positive, and one side is going to be negative. So it has a positive and a negative side, and we call these poles. Just like a magnet. So because of that, water is what? Water is polar. Very good. And we remember the rule, or at least we should remember the rule that I told you, make sure you write down and put on the index card because it's so important. Like dissolves like. So polar dissolves polar and ionic. So if they dissolve each other, they love each other. If they dissolve each other, they mix with each other. If they mix with each other, they love each other. The Greek word for love is philic. Phili or something like that. Philic is to be love-like. So if you love someone, you're philic with them. So hydrophilic means what? Water loving. Water loving. Water loving. Hydrophilic means they love water. So the negative side loves water. It's like Romeo and Juliet. Because the negative side loves water. They're in love. They'll mix all day long. They'll dissolve. They'll become one. Like two people getting married. Easily, these two want to get together. But the problem is the phosphate is attached to a water hating, a water fearing. The word for fear in Greek is phobic. You ever hear phobias? Right. And this is hydrophobic. So it's these fatty acids, lipids in general, are hydrophobic. They hate water. They will not mix, can't stand each other. A true Romeo and Juliet situation. Phosphate loves water, and the lipids hate water. What's a phospholipid gonna do? So if you take a bunch of these, and for right now, let's just all make them saturated. You take a bunch of these and you put them in a glass of water, what's gonna happen? Can you guess? This is a guess. This is something you can guess if you think about it, but you may not be able to. You shouldn't be ashamed if you can't. If you get it wrong, you shouldn't be worried about it. I haven't told you yet. What are they going to do if they fall in water?
They're gonna, I would say like lose like their energy.
Well, they have energy. They're not going to lose it. They might transfer it, but they get some back from water because they're going to bump into everything's going to bump into everything else. So you're right on that. Say what now? Yeah. What's going to attract? What part of this is going to attract the water? The hydrophilic. Excellent. So what will happen is, just out of common sense, the The part that loves water is going to mix with water. They love each other. There's nothing you can do about it. The part that hates water is going to stick up out of the water. It's try to stay away, as far away from water as you can. It's like that, like your best friend's boyfriend that you hate. Like you love your best friend, but you can't stand that guy or that girl. She's too messy. So you stay as far away from her as you can, but you still want to be with your girl or your boy or man or woman or whatever. And so the water loving part points to the water hating part away from the water. Does that make sense? That's what happens to phospholipids when you put them in water, and they'll form a thin layer on top of water. But something interesting happens. Give it some time, and under the right conditions, given enough time and the right conditions, these lipids, these phospholipids, will all of a sudden start to do this. They'll mix with each other. They'll make a circle, because like dissolves like. That means the hydrophilic love the hydrophilic. And what do the hydrophobic do? They stay away from hydrophilic, but what do they do with each other? Like dissolves like. What do? They mix. They fall in love. All the lipids love each other. And if they form a sphere, this is cut, okay? So you have to imagine that you're looking at a sphere, a ball, okay? A ball of lipids where the outside is hydrophilic, the outside's hydrophilic, and the inside's hydrophobic. Does that make sense? Why does that make, why do I say that? Because here, this part is water loving, so it points towards the water. Mainly because it has a phosphate, a PO4, as a negative, has this phosphate sitting there as part of that head, and it's pointing out. The long carbon tails are hydrophobic. This is as far away from water as they can get and still be mixing with each other in this center. This is one drawing of it here. This is another drawing of it here cut open. This is called a micelle. Micelle. It's the first structure that probably formed before life started. This is like, if you're looking at a car, this would be like a spark plug or a piece of metal. It's the component that you need to build the organelle. It's like metal before you can build the carburetor, or metal before you can build the engine. Does that make sense? If you can think of it that way. This is what you need if you're going to build a cell. All right. Do we all have this so far? And I believe this is in your chapter. This micelle is not good enough for life. This is not alive. This is what you call detergent. When you put detergent in your washing machine, this is what you form, these micelles. And what happens is any grease that you have, any oils that you have on your clothes, where do they go? Any hydrophobic stuff that's in your clothes, where do they go? Now I expect you to know this. Like dissolves like. If this is what's in your detergent and you have grease on your clothes, where's the grease going to go?
It's gonna go away, it's gonna go in water.
It's not in the water because it hates water. That's why you can't just wash it without soap. It won't get the grease out. Because water won't, grease, oil and water don't mix. They hate each other. Didn't we just say that? Here you have a micelle. This is what happens when you put detergent in water. Where's the grease on your clothes going to go? Look at it. Think on it.
Is it gonna go like what?
What is the grease? Hydrophilic or hydrophobic? Hydrophobic. What did we say? Like dissolves like.
So does the grease dissolve?
Where? With the other hydrophobic in the middle of the micelle. It's going to go right in the middle of the micelle. And it's going to get stuck there because it doesn't want to come out. And then when you hit the spin cycle and the water comes out of all that water comes out of the washing machine, where's the grease? It's going to come out too in the little micelles. Those little bubbles that you see coming out. You ever see that in your washing machine when it dumps the water? Oh well. You guys need to pay more attention. Those are full of the grease and the dirt. The dirt is dissolved by the water if it's hydrophilic. If it's hydrophobic, it's in the middle of the micelle. Do you see it? In the middle of this ball that I cut open here. But that's no good for life. It's no good for life. Because in order to have life, you have this chaotic place with all kinds of crazy things going on. One of the things that you need to do is you need to have order. You cannot have chaos. Chaos is death. Life is order. So that's characteristic of life number one. You must have order in life. Disorder leads to death. So, two, the second major characteristic of life is you have to have compartments. Why do you need houses? For shelter from what? Rain, snow, well, not necessarily disasters, but because of weather, right? If it gets too cold or too hot. So you have to be able to control your environment, correct? Because otherwise it becomes at least uncomfortable and maybe deadly. If I put you outside naked in the frozen snow, what happens to you? Freeze to death. You know, like that show, whatever, Naked on the Island, they put people. It's on ABC. They don't show anybody naked. They just go naked into the woods.
No, I show like they body, but they blur it out.
But they blur things out, huh? No, I don't watch any of that stuff. I don't watch TV at all. I just saw the commercial for it, and I was like, this just...
You know you paid $6.99 for that little episode?
How you know $6.99?
Hey, I'm just guessing.
No, first of all, I don't know how much it costs. I'm glad you do. But no, I'm talking about like that show that's on regular TV. Thank you very much. Naked and Afraid, I think that's what it's called. Yeah, it's crazy. I saw the commercial for it. I don't watch those things. I don't watch the Housewives of New Jersey. I guess they're gonna have a meeting with the New Jersey I heard it on the radio this morning. I'm like, this is outrageous. Not outrageous. Ridiculous. So anyways, the point is you put outside. Why is that a problem? Because we need a consistent environment. We need to control the environment. We need to be warm in the winter and cool in the summer. Otherwise, if it gets too outside of our normal, we die. Death is no good. Yes? We all agree? Yes or no? Thank you. So compartments allow us to regulate that. But having a single hydrophobic center does not give us compartments. It certainly does separate two spaces, doesn't it? There's a space in here that's hydrophobic and a space out here that's outside. So there's an inside and there's an outside. Okay. but it's not as useful as the following. Something else these lipids can do. These are amazing little things, these little lipids. These lipids can form a bilayer. Bilayer. What do we mean by bilayer? Two what? Layers. It really is not difficult. It really is not difficult. Yeah, it's in the book. It's in the book. That's where you remember it. So what they do is, if you have enough phospholipids, and again, they're under the right conditions, what will happen is something amazing. And again, I do not care if you consider it to be completed by an engineer, like a god, or you think it happened by accident. I don't care. The point is, it happened, okay? And what happens in a bilayer is you have two layers of phospholipids. It's still a ball, it's still a sphere, and I shouldn't even call it a sphere or ball, but it's enclosed, it's three-dimensional. I can only draw it in 2 dimensions. Now I'm drawing it, so there's absolutely no reason why you guys can't draw it. In fact, I'm drawing it, and I'm also erasing and redrawing. So that gives you plenty of time to at least start the drawing. It's a bunch of little circles. They're not perfect. They're going around in a circle. I'm doing it right in front of you in real time, not speeding through it. Shouldn't be anyone not following along. Then in the center, the inside, you have water. Outside, that's H2O. Let me make that a little smaller by zooming in. H2O. There's water inside, and there's water outside. So that's where the blue phosphate heads are pointing towards the water, because they love water. What's in between these two sides? Hydrophobic. They don't like water. Now everybody's happy. The hydrophobic side of the phospholipid get to hang out with the hydrophobic sides. The hydrophilic sides get to hang out with the hydrophilic sides. Now everybody's happy. Again, I'm drawing the lipids.
Would they ever want to combine with each other or not?
What do you mean? What do you mean by combine? They. All right. Say that again. Combine in what way? What do you mean? Will the hydrophilic ever mix with the hydrophobic?
No, I'm talking about the water.
Will the water ever mix with the hydrophobic? They will pass through reluctantly. Not easily. So the answer is they don't like each other, but they will, with enough energy, with enough movement. Remember, everything's moving. That's why we call it a fluid. So there's this layer in the center that's hydrophobic. Hates water, fears water. And this side that's hydrophilic. Loves water. All right. Now you have two actual spaces. Can I use the word, what's another word for, what do you call someone when they go to prison, the place where they live, the room where they live, what do they call it?
A cell?
A cell. A cell actually means a room. That's all a cell means, is room. The first person to look under the microscope, as discussed in your chapter, looked in the microscope and saw little rooms, little spaces in a plant cell. And he called that a cell because that's what a room was a cell. So this is a cell. A cell is something that has a single room, at least. A room. Surrounded by remember, this is three-dimensional, correct? I'm drawing it cut out, but please remember, the cell is actually a ball or some shape. It can be all kinds of shapes, but it's three-dimensional. I'm just cutting it. This cell is cut in half. I'm looking at it like cutting an orange, and I'm looking at the face of the orange. Does that make sense? The flat side of the orange. All right. So, what's the problem here? Well, let's think about it. The water has a bunch of stuff that's dissolved in. There's some sodium ion. There's some calcium ion. There's some glucose out here. Glucose is polar and large. By now, you should know that hexagon is glucose, but I'll go ahead and put GLU for glucose. Sodium ion. And I'm going to write the word ion just so I can emphasize to you that that's what these words mean, that they're charged. Ionic, they have a charge. Ion means a charge. It could be more than one, like in this case it's 2, in this case it's 1, but it's a charge. Polar just means it's pulling partially. So these guys love water. They're ionic, they have a charge, or they're polar, they love water. There's other stuff in here. You might have oxygen gas. Oxygen gas is small, so there's 2 rules for dissolving. If they're really small, or they are nonpolar and medium size, all right, then they can go right through the membrane. They don't need any help. They can go right through here. So this little oxygen molecule is nonpolar. We talked about that. I'm not going to go back and talk about it again. But it's nonpolar and it's small, so it literally goes right through the membrane into the cell. CO2, carbon dioxide, goes right through the membrane because it's small and it's nonpolar. So it goes right through the membrane. It goes both ways. It goes in and out both ways without any problem. They're small and nonpolar. But what about sodium? You eat salt. You crave salt. Why? Because you need salt. How do you get the salt into, this is salt, right? Anything charged in a solution is a salt. Remember that. Remember we defined what salt was. A salt is when a non-metal and a metal come together and one takes the electron, the other one gives it, creating 2 ions, one positive, one negative. The examples were sodium chloride, calcium chloride, remember that? Lithium chloride. So you got all these ions in water. They got to get in. How are they getting in? There's no way. These will not pass through this membrane. Sugar is too big. It will not pass through the membrane. It's not 2 atoms. It's 6 carbons, 12 hydrogens, and 6 oxygens. So it is not going through this membrane easily. What do you need? Wait a second. Read the question. I didn't write the question down. Oh, repeat, yeah. How are you going to get other things that you need to get into the cell, like sodium and calcium and sugar, into the cell, if this is nonpolar and these will not pass because they're big, because sugar is big, and these are charged. They're not passing through the membrane easily. So how do you get them through? How are you going to get them through the membrane?
Well, less like hydrophobic and hydrophobic.
I like your idea. If I put you in a room, now instead of putting you out in the cold, now I put you in a room with a floor, a ceiling, and 4 walls. I put you in. How you getting out? A ceiling, a floor, and 4 walls, made of brick, all made of brick. How you getting out?
If you don't have no like tools, you're not getting out.
Oh, what do you need to get out?
Like
A door or a window is correct. No, I like your hammer idea. You're right. You would need a hammer to get out if you were locked in some kind of. It would be a crypt at that point, right? It's not really a room that we would talk about. So you need to put a hole in this. You need to put a door. What life does is it uses a protein. Uses those amino acids that we talked about and creates a big old molecule, big chain. A big chain. Why does it? Oh, I see. Okay, well, whatever. Makes a big chain of proteins. And the interesting thing about proteins is it has a bunch of different R groups. So some of the R groups can be non-polar. I'm just going to put little blocks for the amino acids. Some of the R groups can be non-polar. They fold like you're foldable. And some can be polar. And they're all linked and they all fold into each other. Again, this is 3-dimensional. And what am I creating when I do this? A door, a way in. All right, we're going to continue this tomorrow, but please make sure you look at this and see what I just drew. Please make sure you understand this because this is a big thing that's tested everywhere. In this case, the protein, I'm going to highlight it here in, let's say, pink. This is a protein. Oh, let me undo that. Highlight it in pink. Oh, no. Highlight it one more time. Highlight it in pink here. This is the protein. It's made of amino acids. It's not made of a phosphate and lipids. So it's not a phospholipid, it's a protein. And because it's a protein, it's made of amino acids, and amino acids can have R groups. Some of those R groups can be nonpolar, like the lipid tails. And because they're nonpolar, those particular why is this not working? Those particular amino acid R groups are going to be nonpolar, so they're going to be dissolved by the nonpolar lipid tails. And they just hang out there. And they anchor the protein there and stabilize it. These amino acids out here are going to be polar. And they're going to be, or maybe they're charged. So either way, they're hydrophilic. They love water. So they hang out with water and away from the lipids. And so the protein basically folds. And by folding, like your little foldable where you made your cards, and cutting them just in the right way, they don't really cut, they just fold. This long chain of amino acids can form a tube. Now this is cut, right? So we cut this in half. So if you were looking down on it, if we change the perspective and you look down on the cell, what you would see is a bunch of phospholipid heads. Yeah?
Go to Miss Donovan. Something was wrong with my report card. And she told
No.
me
We're in the middle class, I'm sorry. So you have a bunch of, this is cells, so this is round, it's three-dimensional. So the heads are going to be out here. And then what's going to happen is in the middle of this, of all these phospholipid heads, you're going to have these hydrophilic, I'm doing them in a square, hydrophilic R group proteins. You know what? Can I do it in a different color? Would that help? Let's make these green. These hydrophilic proteins, let's make them green. Hydrophilic amino acids, they could be charged, they could be polar. They're R groups. Remember that all amino acids, do you remember that? Do you need me to redraw it? So all amino acids are the same except for their R group. And so if that R group is polar or charged, in this case it's green, and if it's non-polar, it's yellow. And so what you see is when you look down on it, these polar amino acids, yes, bless you, hang out with the heads, and the non-polar R groups are hanging out underneath these, as you can see here. Remember, we're looking down at this. This is a downside, looking down. Onto the cell. You see R amino acids with R groups here. But if we look at it cross section, we cut it across and we look at it, you see that the reason this works is that you have R groups that are hydrophobic hanging out with the hydrophobic tail. So like dissolves like dissolves like, all the way around. It's three-dimensional. I got to remind you, it's three-dimensional. Oh, why are you doing that? So it's three-dimensional. So when you look at this, when you look down on it, what this does is it makes a hole. Do you see it? Yes?
Yeah.
Okay, so that's inside. So things can now go into that cell from the outside. So if you have sodium, it might allow calcium. Each one's going to allow different ion. Each channel, we call this a channel. Do you know what a channel is? Not a channel on TV. Do you know what a channel is?
It's like, it has to do with like, the two interviews that you just put out.
Yes, it does. But in general, whenever you have a body of water, like let's say Lake Erie, okay? I should make it blue, I suppose. So you have Lake Erie. And then on the other side, you have, you want a pond over here. But it's empty, it doesn't have water. What can you do?
Fill it up with water.
How?
Take some of
So the land goes up here, and it comes down here like this. And Lake Erie's over here to your left. You want water here, what do?
Take some water out of Lake Erie, like.
You could pump it,
Yeah.
but you can connect them. And the way we connect them is we dig a channel. So we dig a channel.
So the channel is kind of like a tunnel, basically.
Exactly. So then you when you dig a channel, where's that water going to go? It's going to go and fill in the pond. So no, you can go to restroom though and get tissue. It'll fill in your pond through the channel. It's not all going to be liquid over here. On this side, it's going to be land, because the channel's going to go. It's only going to allow water through it, but that channel it's like a river, if you can think of it as a river, but it's a connection. So this is what we call a channel protein. So this is called a channel protein. When you see it on the test, it's going to be drawn something like this. You'll have a membrane. They'll usually draw something like this. It might not be as detailed, believe it or not. It might be just some kind of sketch. And then they'll have something like, do you see how that's a channel protein? Yes or no, please?
Yeah.
All right. Somebody said no, good. Please, if it's no, please say no. So outside, you have sodium that needs to come in. Inside, there's no sodium. How's it going to get in? It can't get through these membranes because remember, these membranes, the internal edge of the internal side of the membrane is hydrophobic.
So what you just drew is a channel protein?
That's correct.
Okay.
So this is a channel protein, a protein that's basically a tunnel, a connection between outside and inside that's going to allow what? What's it allowing?
Energy to come in?
Well, not energy. What is this thing?
A charge?
A charged particle, in this case, sodium. This is sodium ion. But you're right, it's charged. And that's the problem. That's why it can't get through the membrane because it's charged. But with a channel protein, it can get in. And there's even special, each protein can be very special. There's one special protein that you have that only allows sugar through. It's a channel protein that allows only sugar through it. Each protein has a different shape, different size. In this case, only glucose can get through this channel. No problem. And so we make channels for a lot of different things. Is that clear? But channels are basically holes or connections between outside and inside. Doors or windows. Doors or windows. It's selective. These are selective. Selective. So that means the fact that our cells choose what proteins to make allows us to make a selection. Do we allow sugar in today or not? Do we allow salt in today or not? So we make that decision in our cells. Our cells make that decision. Dog cells make that decision. Plant cells make that decision by deciding whether to put that protein in the membrane or not. If you put the protein in the membrane, it's coming in, it can get in. If you're not, it's locked out. What's another word for letting things in?
Another word for what?
Letting things in. What's another word for that?
Accepting?
Accepting, I like that. Accepting, inviting. What's a pathway? Okay. Entering. Anything else? If you're allowed to go in, you're allowed to enter. Okay. What about this word permeable? Well, it's in your chapter reading. Permeable. You never heard of something's permeable? How about impermeable?
Is that the opposite of permeable?
That's correct. Excellent. Good job. Permeable means it's allowed through. Allows things through. Allows things through. It's permeable. But your cell membrane is not permeable. It doesn't just allow anything through. If it did, it wouldn't allow you to keep things out. And you have to be able to keep things out to make the outside different from the inside. If it was just permeable, then the outside and the inside would be the same, correct? And the key to life is that you make the outside different from the inside. That's really what makes us different from everything else in existence. What makes you different from lava or from a rock or from air? The fact that you are what's inside you is different from what's outside you. You can keep you can keep them different because your membrane is not permeable. What it is semi-permeable. I don't like that word semi-permeable because it sounds like you allow half the things through. That's what semi means. But another word that I like a lot better, that you might see either one, so I got to tell you both, is selectively permeable.
Is it like, never mind.
So semi means half. So some people use the word, some books, some people on a test question from the state might use semi-permeable because they're suggesting that it allows some things to, but not others. But I don't like the word because it suggests that it's letting half the things through, which is not true. Your cell selects selectively. Your cell is very selective. It's like going to a club, a fancy club, and in order to get in, you have to be chosen. Okay? So that's what's happening, is that your cell membrane is selectively permeable. It chooses what to allow in and what not, depending on the conditions. So if you have low sugar inside, are you going to let sugar in or not? Yeah. So you let them in, you put the chart. Now you got high sugar, you're done, you don't need any more sugar. What do? Close the door. Take the door. In this case, you take the protein out of the membrane, you remove the door. So you move the channel, the sugar can't get in. You need more sugar, you put the channel back in. Does that make sense? That's how this works. This is how you allow things in and out. This is how a membrane can be selectively permeable. Now, I wish that was that simple, and that was all there was to it, but it's not. There are a couple other proteins we should talk about before we go on to see how things move across the membrane. That, by the way, this idea, all this is so that you can understand two words. Two words and two concepts that you're going to be tested on with problem sets. You're going to have problems you're going to have to solve. The two words are diffusion. Anybody read the chapter know what the other word is? Nobody's read the chapter. Okay. Osmosis. Diffusion and osmosis. In order to understand those, you have to understand how that membrane works. So pay attention to these details. They're important. The more you understand here, the more you'll understand these two very important words that they test the heck out of you on the OST. All right. Let's take a look at how things, first let's look at another kind of protein. So this is just a channel. Now there are other kinds of channels. There are other kinds of proteins. There is a type of protein that is actually closed off. There is a channel, there's a hole, but there's a door to get in. There's a door that you have to open. And that door has a key. These are molecules, obviously. This is a protein again. I'm not going to draw the little blocks, but these R groups are hydrophobic. And why do they have to be hydrophobic? Because these lipids are hydrophobic and they're dissolving each other, so they have to be hydrophobic. This door only opens with the key, but these other R groups are hydrophilic because they're hanging out with water. Now you see the channel, correct? You can get through, but you have a door stopping it. That door, one of those doors that opens, it has a lock. That lock is called a receptor. That lock is called a receptor. That receptor will only open, that will only react. It's a receptor. Only reacts to a specific key. So this is the receptor, and usually there are several words that people might use, but the receptor requires a signal. You need a signal molecule. Another word for that is a key. All right. So you have this signal molecule, the shape. You see how this is round and you see how the receiver is round? That receptor does not have to be round. That receptor could be square. That receptor could be triangular. That receptor could have all kinds of funky shapes. But the key has to fit perfectly, just like the key that goes into your house. Does that make sense to you? Is that making sense, guys, or not? All right. So that receptor, that signal is often called a ligand. And we call it a ligand because it attaches to the receptor. I'd rather they just call it a key, but they call it specifically a ligand. Usually it's a protein. Sometimes you might know the word, that signal molecule, sometimes that signal molecule is something called a hormone. You've heard of a hormone before, right?
Yeah.
So sometimes it's called a hormone. It depends on what the key is. Some keys, some ligands are hormones. Other keys are not hormones. You've heard of there's another possibility. Have you heard of something called neurotransmitter? Have you heard of something called dopamine? All right. Or acetylcholine. You've heard dopamine's the happy chemical that's in your brain, makes you happy. It can make you, it's what drugs like heroin replace. They turn on your dopamine receptors. In any case, neurotransmitters are what allow you to think. They're what sends a signal down your neuron. It's what allows your brain to work. So they are signals that your brain cells send to another brain cell. We'll talk about that, how that works later. So that's called a ligand-gated channel. It's a gate, right? The door is a gate. So we call it a ligand-gated channel. There's one last kind I want to talk about when it comes to this type of movement across the membrane. So I'll wait till you finish that. Are we ready? So there are other kinds of gates that only open when you have a voltage change. Now we have to go back to middle school vocabulary and look at this word, volt. You should have learned that in your middle school curriculum. Anybody know what volt? You've heard of it, I know. And you either don't remember it or the teacher didn't get to it, that's fine. But this is a word that you should know. You've seen it on batteries. right? The word volt. There's even a car that's named Volt, or used to be anyways. The question is, what is volt? And what is a battery? Anybody know what a battery is? Oh, you do? What is it? What is a battery? I like charge. I like that word charge. Something that what now? So, something that uses power. I like that. It actually stores power. Can we say that? Yeah. You charge it, right? Somebody said charge it. So you fill it up with power. But what is it charging? What are you putting into it? Electric? What's electric? What is electric? Think of the word. I've told you this before. What is electric? Electrons. That's right. Electrons. That's where we get electricity from. They're electrons. Little negative charges. Little particles that have a negative charge. That's it. That's all it is. Inside a battery, you have, I'm just going to draw a C battery here. Let's do a square battery. You've seen the square ones because you're going to be using the square ones in a lab, so might as well draw a square one. One side is of the battery is positive, has some chemicals that have a positive charge, and the other side has some chemicals that have a negative charge, and in between, we separate the charge, the materials with a divider. Doesn't allow the two to mix. So on one side it's positive, and on the other side it's negative. Do you see that? So we have poles, right? Negative and positive pole. Correct? That's how your battery works in your phone. Plug this in, will you? All batteries work the same. You got the only difference is what kind of chemicals are you going to use? You are using lithium ion. That's what your batteries are. Your batteries are made of lithium ion. That's Li+1. Thank you. On the other side, some other chemical that's negative. Then you take a wire, correct? That's how you make a battery work. Do y'all agree? In a wire? Is that how you make a battery work? You need metal? Have you used a battery? Why do you look at me like you've not used a battery before? You've used a battery. Okay. So you're taking, you put, now in a machine like your phone, you don't see the wire. What you see is if you look at your phone where you take the battery off, you see a little metal tip. That metal tip is connected to a little line of metal that they soldered. They just put a little bit of metal inside for argument's sake, let's just call it plastic. Inside on a plastic plate, we call it a circuit board. You just have this little square plate, and on this plate, if you ever looked inside your phone or inside any electronics, you'll see a bunch of circuits. Maybe there'll be a little doodad here. It's a resistor. There'll be another circuit. Now everything's digital, so everything's printed. They print this with metal, little strips of metal. It's just strips of metal. They replace the wires with little metal strips, and then they'll have like a little CPU here. Maybe there'll be a little processor over here. And these are called circuit boards. Have you seen these before? All right. And those of you going to the IX Center, you might see them there. All right, because you guys are going to do programming, computer programming stuff there, informational technology. They might have some displays of circuit boards. And when you plug in your battery for your phone, what you're going to find is you're going to have one side here where your battery connects to, and maybe your battery is going to, I'll just make a square battery. It has to be metal to metal. Metal must touch metal. And your battery might be long like this. And then on this side, you have another terminal, opposite terminal. One's positive, one's negative, that touches this metal part. Has to be metal to metal, but other than that, it doesn't matter if it's a wire or what have you. But as soon as you get metal to metal contact, what's going to happen? What's going to happen? What are the electrons going to do? What do electrons do? What does electricity do? How does you guys plug things in all day long? How do you not know that? I don't understand.
What electricity do with batteries?
How does electricity work?
With energy.
Okay, what does that mean? It uses electricity.
Energy gives them power.
These are words. They're not describing anything. You're using words. You're just throwing words out. So what? I'm putting a light bulb here. All right, you should have done this lab in middle school. I am so sorry that you didn't do this, but we have to catch you up. So I have to go quickly. Hurry up, because I don't want you to miss this, especially if you don't know it. You did do this in middle school? Okay, so what happens when you connect the wires from the positive to the negative? The metal's connecting it. What's going to happen? No, it's not. It's going to discharge. It's going to be opposite from charging. Connect the two wires together. What's going to happen? Quickly guess, because I'm going to tell you in a second. I connect the wire from the negative to the positive in any machine that uses electricity. I connect the battery to the wire. What's going to happen? Okay, it's going to give its power, but how? From the battery, correct, but how? What's going to happen is electrons are going to start to move. They're going to flow. Flow, literally like water, of electrons. That's called a current. Just like the flow of water, it's called a current. That's what happens when you stick your finger in a socket. Don't do that. Stick your tongue in the socket. What's going to happen is electrons are going to flow from the wire onto your tongue, from the negative to the positive. Is that clear? And what's going to happen to your tongue? Well, it's going to resist that movement because your tongue's not made of metal. It's not going to want the electrons to flow through. It's not very conductive. We call it conductive. So it's going to resist it, which means heat's going to build up and you're going to burn. Is that clear? But we don't stick our tongues in electricity. In a small battery like this, it wouldn't burn. It would just shock you. You would just feel a shock. That shock is just electricity flowing across your cells. Your cells are made of fat, which acts a lot like rubber. Rubber does not allow electricity to flow. The fat in your cells doesn't allow electricity to flow either, right? It doesn't allow charged particles through, correct? Because it's nonpolar. We all agree on that? Okay. But this is metal. Metal allows things to flow. So these electrons that are on this side are going to flow. That's what this yellow line is. It's going to go across this. In this case, this light bulb, there's a little filament here. Do you see this filament? Little piece of metal here that's not made of copper. This is a copper wire. Copper lets things flow no problem. This is made of a metal that doesn't like to let electricity flow. It'll let it flow, but not well. So it gets real hot. And then what happens when it gets hot? It lights up. That's how we get light from a light bulb. You get the little piece of metal in these types of bulbs. There's two different kinds of bulbs. We use fluorescent bulbs here. They're different, but it's a similar idea. The flow of electrons excites the material and makes it glow. And we call that light. Now, the electricity keeps flowing from positive to negative. It's the flow of electrons that excites the material and it glows. But the electrons have to keep moving because if they stop flowing, the light goes out. Now here on a switch, this is AC. This is connected to a generator. Our power company is burning coal or using nuclear energy to boil water to move turbines that makes electricity constantly. So as soon as you flip a switch, the electricity is there waiting to flow. But here in a battery, you store that electricity, like in your phone, you store it here. You push the electrons from here the opposite direction when you're charging it, and you fill this side up with electrons. So it's like you're taking something heavy and you're putting it up real high, so you're getting ready to take advantage of it falling. So you push it high so it can drop. So when it drops, you can use the energy of it dropping to run your machine. Yeah.
When the light bulb goes out, does that mean we can turn on current or
I love that idea. That question. It's a great question. If this type of light bulb goes out, what happened is the metal burned. The reason the metal doesn't normally burn, it doesn't burn for a long time, we call it burned out. The bulb's burned out. The reason it doesn't normally burn is that there's no oxygen in here. They took all the oxygen out. For something to burn, you need oxygen. That's how electrons work. This is called, before you go, the flow of electrons is called current, and that is kinetic energy. When you store electrons, the difference between these two sides is called electrical potential energy. Yeah, I'll be posting it online. Please watch it. Guys, you're going to run out of time. It's not going to be a happy scene for your grades if you don't get this done. You need that workbook for your lab. If you lose it, you're not getting another one. We don't have another one. Put it in your binder. On your phone, what you're doing is you're exciting a gas. So when you're using instead of a metal that gets heated up on your phone, there's a gas in your screen or a liquid that gets excited. It's if you have an OLED or it depends on what kind of screen you have. This electrons flowing through the material makes different places, makes different parts of it glow, and that's how you get a picture. Now, sound get by going through a different kind of the same electrons flowing through a different part of your phone makes microwave energy, and those microwaves go to a tower, and they send your signal, your voice signal, your text signals, or whatever, to the tower that sends it to your friend's phone. That's why it's not a great idea to keep your phone up to your face all the time, because you're microwaving your brain, and your brain cells are sensitive. So you might want to use an earbud or talk on a speakerphone. You could use it, but don't try not to use it too much.
So how long would it take for somebody for their brain to be microwaved completely?
No, that wouldn't happen. Not like in a microwave oven. But what could happen is you could develop cancer over time, brain tumors, and that's what some physicians think might happen. So you need to keep the phones away from you. This is microwave energy. Same stuff. Think about what you do when you heat up your food in the microwave. You're doing it at much lower power, right? So you're not cooking your brain, but you are exposing it to microwave energy. I hate when that splashes. All right. So that's the flow of electrons. That's what we call kinetic energy. Do you agree? The flow of electrons are doing what? What are the electrons doing if they're flowing?
Rubbing against each other?
Yeah. So what is that? Friction. But what? Friction because they're rubbing. What do we call that? Movement, which means kinetic energy, correct? When we're storing, when there's a difference between positive and negative, when you're storing the electrons, when you're shoving them into one side and making one side negative, you're getting ready to release them, right? We call that potential energy. Do you remember potential energy and kinetic energy from middle school? And I think what they taught you in middle school is that potential energy, they should have, my understanding is they should have talked to you about electrical, but potential energy as well. But if you put a ball up here, then this has a lot of potential energy, correct? And as it starts to roll down the hill, let me do a dotted line. Here, as it rolls down, you're exchanging the potential energy for kinetic energy. So about halfway down, you got half the potential energy is gone, and you still have half the potential energy left, and then half the energy is kinetic energy, correct? Do you remember that? Then at the bottom of the hill, what do you got? It's 100% what? Kinetic, so it's going as fast as it's going to go, and 0% potential energy because it's at the bottom of the hill, not at the top. Does everybody agree with that? Okay. But this is electrical potential energy, so you're not talking about height. Here you're talking about how big a difference you have. The bigger the difference between positive and negative, the higher the electrical potential energy. So if you have a big difference, there's a lot of flow. So which would you rather have if you want a good flow of electrons? Do you want a 12-volt battery, or 12 or a 9? I should tell you, the word volt, the symbol is V, is electrical potential energy. The larger the number, up arrow means larger, the larger the number on the battery, the larger the X volts, right? The larger this number here, the bigger the difference is between the positive and the negative. Okay? So if you have a 9-volt battery, that's a unit of measuring telling you there's 9 units difference from the positive and the negative. If I have a 12-volt battery, what does that tell you? Oh, I put 10. I don't know why I put 10 when I said 12. I don't understand why I do things sometimes. 12-volt battery. The difference between the two sides is what? And in a 12-volt battery versus a 9-volt battery. What's the difference in 12? It's 12. Is that making sense? Because you guys you're very quiet. So you have two sides. I'm gonna draw a battery again. Any battery has two sides. If you have a battery, it has to have two sides. This is important. It's an important idea. That's why I'm spending so much time on this. You have a positive side and a negative side. We all agreed on that, right? That means these sides are different, correct? Yes? Okay. So what's the difference between the different? The higher the difference, the larger the volts, the more power is stored. This is potential energy, right? So the larger the number, the more potential energy. So the higher the difference, the higher the potential energy here. So a 9-volt has a difference of 9. What does that number really mean? Don't worry about it. It's just the number 9, okay? Versus a 12-volt, which tells you what? There's 12 units of difference. Do you agree? Okay. Now, it's the same with potential energy that you learned in middle school. Think about it. If I have a rock that's at the top of a hill that's 10 meters high, right? And versus a rock at the top of a hill that's 5 meters high, which has more potential energy?
10.
The 10, because the number is bigger. Does that make sense? All right. It's the same thing here. The bigger the difference, the larger the number. In your car, you have a giant 12-volt battery. Huh? I don't know. Do you? What time is it? Is it time to leave? Yeah. If it's time to leave, you go. Regular time. There's no change in your schedule. I don't know where you're going, though, because if you have anyone who's on a field trip, they have a sub for you.
Adam.
I think you go wherever they have a sub.